2 trillion galaxies. That's what lives inside our observable universe, a sphere 46.5 billion light-years across. It sounds like everything. It sounds like more than anyone could ever need. And it is, genuinely, staggering. But here's what nobody mentions right after they say that number. It's almost certainly a tiny fraction of what actually exists. Not because our telescopes are too small, because the physics that made our universe livable also guaranteed that most of it would be hidden from us, on purpose, structurally, baked in. And tonight, we're going to follow that math all the way to the edge and then past it as far as the equations let us go. Get comfortable, hit subscribe. You're going to want to be here for this. Part 1. The knife edge we shouldn't be on. There is a number so precise, so impossibly exact, that when physicists first calculated what it should be versus what it actually is, some of them genuinely wondered if the universe had been set up by something that knew what it was doing. That number is called omega. And omega describes the shape of everything. Not the shape of a galaxy, not the shape of a supercluster, not even the shape of the observable universe in the conventional sense. Omega describes the overall curvature of space itself, the geometry of the cosmos at the largest scale we can measure. And when the Planck satellite, the most precise cosmic measuring instrument humanity has ever built, came back with its final data, the value it returned for omega was 1.000 plus or minus 0.005. In other words, the universe is flat, not roughly flat, not approximately flat, flat to within 0.5%, measured across a sphere 93 billion light-years in diameter. Now, before you move on from that sentence too quickly, let's sit with it for a moment. 93 billion light-years. A single light-year is about 5.88 trillion miles. Multiply that by 93 billion, and you have a number so large that if you tried to write it out in standard notation, the ink would run dry several times over. Across that entire expanse, across a volume of space so enormous that the human mind genuinely cannot form a sensory picture of it, we have measured the geometry of reality and found it balanced on a knife edge with a precision of 0.5%. That should bother you, not in a frightening way, but in the way that a magic trick bothers you when you cannot figure out how it was done. Because here is the thing about flatness in cosmology: it is not a stable condition. It is not a resting state that space naturally settles into over time. It is the opposite of that. Flatness, in the equations that govern the evolution of the universe, is what physicists call an unstable fixed point. Think of it like trying to balance a pencil on its tip. You can do it for a moment with extraordinary care, but the slightest nudge in either direction sends it falling, and the longer time passes, the further from vertical it gets. The universe works the same way. If omega had started out even slightly above 1, even by a tiny fraction, the self-gravity of everything in existence would have been just strong enough to win the war against expansion. Space would have reached a maximum size and then collapsed back inward, ending in what cosmologists call the Big Crunch. We are talking about a universe that might have lived for a few 100,000 years, maybe a few million, before folding back on itself into nothing. No stars, no planets, no anything with enough time to form. And if omega had started slightly below 1, the opposite catastrophe would have played out. Expansion would have won decisively. Space would have stretched apart so quickly that matter never had the chance to clump together under gravity. You would have ended up with a universe of thinning, cooling gas spreading outward forever into a featureless, dark emptiness. No galaxies, no stars, no carbon, no you sitting wherever you are right now, watching this. The window between those two outcomes, between collapse and eternal dispersal, is extraordinarily narrow. And here is where the number becomes staggering. For the universe to look as flat as Planck measured it today, for omega to be that close to 1 at this moment in cosmic history, the initial value of omega at the very first instant of the universe at what physicists call the Planck time, 10 to the power of negative 43 seconds after the beginning would have had to be equal to 1 to within 1 part in 10 to the power of 62. Write that out. 1 followed by 62 zeros. That is the denominator of the precision required. That is how impossibly exactly, the initial conditions of the universe needed to be calibrated for everything you see around you to exist. If the initial omega had differed from 1 by even a single unit in the 62nd decimal place, the universe would have either collapsed or dispersed long before a single star ever ignited. This is what cosmologists call the flatness problem. And calling it a problem is something of an understatement. It is not the kind of problem where you shrug and say the universe just happened to start that way, because that answer, taken seriously, requires you to accept that out of all the possible starting configurations for a universe, the effectively infinite range of values that omega could have taken, the one that actually occurred was so finely tuned that it makes winning the lottery 17 times in a row look like a statistical certainty by comparison. The flatness problem is not a puzzle about measurements being slightly off. It is a puzzle about why the universe should not exist in the form it does. And here is where the story begins to open up into something much larger. Because physicists did not simply throw their hands up at this impossibility, they found a mechanism, or rather, they proposed one. A mechanism so extreme, so violent, and so brief that it left almost no direct trace in the observable universe, yet whose consequences are written into literally everything we can see. That mechanism is called cosmic inflation. And once you understand what inflation actually does, not just to the flatness problem, but to the very boundaries of what is observable, the universe starts to look very different from the one most people picture when they look up at the night sky. Inflation is not a gentle process. It is not the ordinary expansion of space that has been going on for the last 13.8 billion years. Inflation is a period in the very early universe, lasting somewhere between 10 to the power of negative 36 seconds and 10 to the power of negative 32 seconds after the beginning, a window so brief that expressing it in human timescales is almost meaningless, during which space underwent exponential expansion on a scale that has no analogy in anything we experience. The universe grew by a factor of at least 10 to the 26th. Some models suggest far more. To get a feel for that number, if you took a single atom, something already invisible, already beyond the threshold of direct human perception, and inflated it by that factor, it would end up larger than the entire observable universe we see today. What inflation does to the flatness problem is elegant in its brutality. Imagine you are standing on the surface of a sphere. If the sphere is small, the size of a basketball, the curvature is obvious. You can feel it underfoot, you can see it at the horizon. But as the sphere gets larger, the curvature becomes less apparent. The surface starts to feel flatter and flatter from your vantage point. By the time you are standing on something the size of Earth, the ground feels completely flat, even though you are actually living on a ball. Now take that process and multiply it by 10 to the 26th. Any curvature that existed in the early universe, any deviation from flatness that omega might have started with, would have been stretched so completely, so overwhelmingly, that from our vantage point inside the post-inflation universe, it would be undetectable. Inflation does not require omega to have started exactly at 1. It takes whatever starting value omega had and drives it to 1 with such force that the original value becomes cosmologically irrelevant. Inflation solves the flatness problem, but solving a problem in physics rarely comes for free. Every solution costs something, and what inflation costs is something most people have never fully reckoned with. Because if inflation stretched space by a factor of at least 10 to the 26th, that stretching did not stop neatly at the edge of what would later become our observable universe. It stretched everything. It stretched regions of space that were, before inflation, in causal contact with our region. Regions that could theoretically have been seen or interacted with, and pushed them so far away that no signal travelling at the speed of light will ever reach us from them. Not in 1,000,000,000,000 years, not in 100,000,000,000,000 years, not ever. The universe we can see, the sphere 93 billion light-years across, containing roughly 2 trillion galaxies, is not the universe. It is a tiny patch of a much larger structure. And that larger structure was hidden from us, not by accident, not by a lack of telescope power, but by the very same physics that made our existence possible in the first place. The thing that solved the flatness problem is the same thing that guaranteed we would never see most of reality. There is a calculation that tries to put a lower bound on how large the actual universe must be. Researchers Vardanyan, Trotter, and Silk published their Bayesian analysis in 2011, working from the flatness constraints in the Planck data, and what they found was that under the simplest inflationary models consistent with what we observe, the real universe must be at least 251 times the radius of our observable sphere. 251 times. That translates into a volume roughly 10 million times larger than everything we have ever seen or mapped. And that is the minimum. That is the conservative number. Under many reasonable models, the actual size is incomparably larger than that possibly infinite. This is not fringe science. This is not the speculation of a theorist on the margins of the field. This is what you get when you take the Planck satellite's measurements seriously and follow the mathematics wherever it leads. The conservative reading of mainstream cosmology is that we are trapped inside a causal bubble, a sphere defined not by the extent of the universe, but by the distance light has had time to travel since the beginning and beyond. That bubble lies a structure so enormous that describing it as more universe barely captures what we mean. So here is the question that will thread through everything we are about to discuss. What kind of physics creates a universe where most of it is permanently hidden from anyone who could ever look? Not hidden by accident, not hidden until we build better instruments, but hidden by structure, hidden by the very equations that govern how space grows. That is what we are going to find out. And I will warn you now, the answer does not get more comfortable the closer you look. It gets stranger. Part 2. The sphere you are trapped inside. Let's get specific about where you are. Right now, as you watch this, you are sitting at the exact center of a sphere with a radius of approximately 46.5 billion light-years. Not near the center, not close to the center, at the precise geometric center. And so is every other observer in the universe, no matter where they are. That is not a philosophical statement about human specialness. It is a direct consequence of how observation works in an expanding universe, and understanding it properly is the first step toward grasping just how much is hidden from us by the physics of inflation. The observable universe is defined by a simple constraint. The distance light has had time to travel since the universe became transparent, roughly 380,000 years after the beginning, when the cosmos cooled enough for electrons and protons to combine into neutral hydrogen and stop scattering every photon that tried to move. Before that moment, the universe was a plasma, an opaque fog of charged particles so hot and dense that light could not travel freely through it. After that moment, photons were released and began their journey. The most ancient photons we can detect, the ones that have been traveling toward us since that very moment of transparency, have been in transit for 13.8 billion years. They are the oldest light in the universe. But here is where intuition breaks down, and it is worth pausing on this because it trips people up every time. Those photons did not travel 46.5 billion light-years in 13.8 billion years by moving faster than light. Space itself has been expanding the entire time they were traveling. The universe kept growing while the photons were in motion, stretching the distance between their origin point and us. By the time they arrive, the object that emitted them is now about 46.5 billion light-years away in what cosmologists call comoving distance, the distance accounting for expansion. This is the difference between the light travel distance and the actual current distance, and it is crucial. The edge of our observable sphere is not 13.8 billion light-years out. It is 46.5 billion light-years out, because the universe kept growing while the light was crossing it. Every observer in the universe, no matter where they are located, sees themselves at the center of their own sphere of this size. An alien civilization sitting in a galaxy near what we perceive as our observable edge has its own observable sphere centered on itself, overlapping with ours in some regions and extending far beyond ours in directions we cannot see. Their sky contains galaxies we have never seen and never will, and their observable sphere is just as complete seeming from the inside as ours is. This is the illusion of totality, the way a finite local window onto a larger structure can feel from the inside, like the whole thing. Inside our sphere, the numbers are extraordinary. Recent estimates, building on the work of Consolis and colleagues published in 2016, suggest there are approximately 2 trillion galaxies within the observable universe. 2 trillion. For context, if you tried to count them at 1 per second, without stopping, without sleeping, without pausing for any reason, it would take you over 63,000 years to reach 2 trillion. The Milky Way alone contains somewhere between 100 billion and 400 billion stars, and the Milky Way is, cosmically speaking, a fairly ordinary galaxy, not the smallest, not the largest, just one of 2 trillion. The observable universe contains, by most estimates, somewhere in the range of 10 to the power of 24 stars. That is a 1 followed by 24 zeros. More stars than grains of sand on every beach and every desert on Earth combined, multiplied several times over. And yet, as we established, this is a tiny fraction of the total. The central thread running through everything we are exploring is the consequence of inflation, that the same mechanism which solved the flatness problem also pushed the overwhelming majority of reality beyond any horizon we can ever reach. Those 2 trillion galaxies are the local neighborhood. The full structure is something we can only infer from the physics, never observe directly. The boundary of our observable sphere has a name and a physical reality. It is called the cosmic microwave background, and it is one of the most extraordinary things in the sky, not because of what it is, but because of what it tells us about the limits of our view. The CMB is not a wall, and it is not empty space. It is the surface of last scattering the shell of the universe at the moment it first became transparent. Every direction you look in the sky, if you could tune your eyes to the right frequency, you would see this glow, a nearly perfect black-body radiation field at a temperature of 2.725 Kelvin, or about negative 270.4 degrees Celsius, barely above absolute zero. The CMB is not the edge of the universe. It is a time boundary, the furthest back in time we can see using electromagnetic radiation of any kind. Beyond it, in every direction, space continues. It continued before the universe became transparent in the form of that opaque plasma, and it continues beyond the range of the CMB in the sense that after inflation, vast regions of space were pushed outside our causal contact entirely. The CMB is not where the universe ends. It is where our line of sight ends, for now, using light. There are signals that come from beyond the CMB in the sense of being older. The cosmic neutrino background, for instance, decoupled from matter about 1 second after the beginning 380,000 years before the CMB photons were released. Neutrinos barely interact with matter at all, so they streamed free much earlier. In principle, detecting that background would let us see the universe as it was in its first second. In practice, we have not yet built a detector sensitive enough to capture it directly, though its presence is inferred from the CMB data itself and from our models of early universe nucleosynthesis. And even beyond the neutrino background, there are gravitational waves from inflation itself, ripples in the fabric of space-time, generated when inflation stretched quantum fluctuations to cosmic scales. These gravitational waves, if detected, would be the most ancient signal possible, encoding information from the inflationary epoch itself. We have not directly detected them yet, though indirect evidence in the CMB's polarization pattern, specifically a component called B-mode polarization, may eventually reveal them. The night sky, then, is not a window onto the universe. It is a partial map, a local record, a two-dimensional projection of a sphere that is itself just one region of a far larger structure. The familiar feeling of looking up and seeing the whole cosmos spread out above you is an illusion produced by the limits of our observation. You are seeing your neighborhood. You are not seeing the city, let alone the continent, let alone everything that inflation stretched beyond your reach. And the reason that larger structure is hidden is precisely the reason it could support your existence at all, because inflation stretched it flat, stretched it smooth, and in doing so, stretched most of it past every boundary you could ever cross. The observable universe is not a description of what exists. It is a description of what the physics of space-time permits us to reach. Part 3. The Four Horizons and Why They Don't Agree. One of the most persistent confusions in cosmology is the idea that there is a single edge to the universe, a line somewhere out there beyond which nothing exists, or beyond which our telescopes simply cannot see. The reality is more complicated and considerably stranger. There are actually several different horizons in cosmology, each defined by a different physical constraint, and they do not agree with each other. Understanding why they differ is essential for understanding what inflation actually did, and what it means for the permanent hiddenness of most of reality. The particle horizon is what most people mean when they talk about the observable universe. It sits at approximately 46.5 billion light-years and marks the farthest distance from which light could have reached us in the history of the universe, accounting for expansion. Anything within this sphere has, at some point, been in causal contact with us. Information could have traveled between us and those distant objects at least once. This is the horizon shaped directly by the age of the universe and the rate of its expansion. Inflation determined its character by flattening and smoothing the region we inhabit, and by establishing the initial conditions from which everything inside this sphere evolved. But then there is the cosmic event horizon, which sits at a much closer distance of about 16.6 billion light-years. This is not the horizon of what we can see. It is the horizon of what we can ever interact with, the boundary beyond which, given the current and projected future rate of cosmic expansion driven by dark energy, any signal we send today will never reach its destination, and any signal sent from beyond this point will never reach us. It is a horizon defined not by the past, but by the future, by the acceleration of expansion that is actively widening the gulf between us and distant galaxies. The Hubble sphere is different again. It sits at about 14.4 billion light-years and marks the distance at which galaxies are currently receding from us at exactly the speed of light. Inside the Hubble sphere, galaxies move away from us slower than light. Outside it, they recede faster than light. This does not violate relativity. It is space itself expanding, not objects moving through space, but it does mean that photons, currently outside the Hubble sphere but trying to reach us, are actually losing ground. They are moving toward us through space, while space itself carries them away faster than they can approach. Eventually, as the universe expands, the Hubble sphere grows, and photons that were initially losing ground find themselves in a region of slower recession and can finally start making progress. And then there is the future visibility limit, about 62 billion light-years in co-moving distance, which marks the farthest objects that will ever become visible to us as the universe ages, including photons currently in transit that have not yet arrived. Here is what ties all of these together and brings us back to the central story. Right now, we can see galaxies, some of them clearly, in beautiful detail that we will never be able to visit, never be able to communicate with, and that will eventually disappear from our sky entirely. Dark energy is accelerating the expansion of space. Over time, distant galaxies will redshift beyond detectability, their light stretching to wavelengths too long for any instrument to capture. The observable universe, in causal terms, is actually shrinking, not in the sense that the sphere of past visibility is getting smaller, but in the sense that the set of objects we can ever hope to interact with is contracting. Inflation set the initial scale of what is hidden. Dark energy is continuing to hide more of it as time passes. The boundary was built into the physics of this universe from its earliest moments, and it is being reinforced by every second of ongoing expansion. Part 4. Drawing triangles across the universe. Here is a question that sounds absurd on its face. How do you measure the geometry of the universe? Not the shape of Earth, not the curvature of space-time around a massive object, but the overall global curvature of the cosmos itself. How do you draw a triangle big enough to test whether the angles add up to 180 degrees or something different? The answer involves the cosmic microwave background, and it is one of the most elegant pieces of observational cosmology ever attempted. In a flat universe, the rules of Euclidean geometry apply at the largest scales. The angles of a triangle add up to 180 degrees. Light travels in straight lines that stay parallel. But in a positively curved universe, one with omega greater than 1, like the surface of a sphere, parallel lines eventually converge, and the angles of a large enough triangle add up to more than 180 degrees. In a negatively curved universe saddle-shaped, with omega less than 1 parallel lines diverge, and triangle angles sum to less than 180 degrees. The CMB gives us a ruler. In the very early universe, before the surface of last scattering, sound waves were traveling through the hot plasma pressure waves, driven by the competition between radiation pressure pushing outward and gravity pulling inward. These waves had a characteristic scale determined by how far sound could travel in the age of the universe at that time. When the universe became transparent and the CMB was released, those sound waves froze in place, leaving a pattern of slightly hotter and slightly cooler regions imprinted across the sky. The characteristic scale of those frozen waves, the distance between the peaks and troughs, is known extremely precisely from first principles of plasma physics. It acts as a standard ruler. Now, if you know the physical size of that ruler, and you can measure the angle it subtends across the sky, the angle it appears to span from our vantage point, you can calculate the geometry of the space through which its light has been traveling. In a flat universe, a ruler of a given physical size at a given distance will appear at a specific angular size. In a positively curved universe, it will appear larger. In a negatively curved one, it will appear smaller. This is the cosmic triangle test, and the CMB angular power spectrum, the pattern of peaks and troughs in its temperature fluctuations, carries the answer. The first major modern result came from the Boomerang experiment, a balloon-borne observatory that circumnavigated Antarctica in 1998 and 2000, measuring the CMB at degree scales with unprecedented resolution. Boomerang found that the first acoustic peak in the CMB power spectrum sat at a multipole moment of approximately 220, exactly where flat geometry models predicted it. Then came WMAP, the Wilkinson Microwave Anisotropy Probe, which operated from 2001 to 2010 and refined those measurements dramatically. And then came Planck, the European Space Agency satellite, that operated from 2009 to 2013 and returned the most precise CMB data ever collected. Planck confirmed flatness At the level we have already discussed, omega equals 1 to within 0.5%. The acoustic peaks fell exactly where flat geometry models predicted. Independent confirmation came from baryon acoustic oscillations, the same frozen sound waves detected not in the CMB, but in the large-scale distribution of galaxies. The pattern of galaxy clustering across the universe carries an imprint of those early pressure waves, and that imprint, measured across surveys of hundreds of millions of galaxies, agrees with CMB flatness measurements to extraordinary precision. But there is a wrinkle, and it is the kind of wrinkle that keeps cosmologists awake at night. The Planck data showed a slight anomaly in the lensing of the CMB, the way the CMB's temperature pattern is blurred and shifted by the gravitational pull of intervening matter. The lensing signal was slightly stronger than flat geometry models predicted, hinting at roughly 2 to 3 sigma significance, not enough to declare a discovery, but too large to ignore at a slightly positively curved universe. If real, this would push omega just above 1 and imply a finite spherical universe rather than an infinite flat one. The tension has not been resolved. Combined datasets that include galaxy surveys and baryon acoustic oscillations still favor flatness. But the Planck lensing anomaly is a persistent reminder that our measurement, as precise as it is, still carries uncertainties, and the implications of those uncertainties, as we will see, are enormous. Because this is exactly where the connection to inflation becomes critical again. The extreme flatness that Planck measured, that precision of 0.5% across the entire observable sphere, is not something that could exist without inflation or something functionally equivalent to it. Classical Big Bang cosmology, without an inflationary phase, cannot produce a universe this flat. And inflation, as we have established, does not stop at the edge of our observable sphere. It stretched far beyond it. The same measurement that confirmed flatness is the measurement that implies everything we cannot see. Part 5. The flatness problem. Why this shouldn't exist. Let's go deeper into the mathematics of why flat is so dangerous. Because I think it is easy to hear 1 part in 10 to the 62 and let it wash over you as just another big number in a field full of big numbers. It is not. It is something categorically different from other fine-tuning results in physics, and sitting with it properly is essential for understanding why inflation is taken so seriously by so many physicists. In standard Big Bang cosmology, without inflation, omega obeys a specific evolution equation as the universe expands. The deviation of omega from 1, let's call it the quantity, omega minus 1, grows with time during the matter-dominated era, and grows even faster during the radiation-dominated era that preceded it. What this means, technically, is that omega equals 1 is an unstable fixed point in the dynamical equations. Just as the pencil balanced on its tip will always fall, a universe with omega even slightly away from 1 will evolve away from 1 over time. The deviation doesn't stay small, it grows. Run that equation backward in time. Today, omega equals 1 to within 0.5%. Go back 10 billion years to the era when the first stars were forming. Omega had to have been even closer to 1 at that point. Go back to the epoch of Big Bang nucleosynthesis, about 3 minutes after the beginning, when the first protons and neutrons were fusing into helium and deuterium. At that point, omega had to equal 1 to within roughly 1 part in 10 to the 15th. Go back to 1 second after the beginning, 1 part in 10 to the 18th. Go back to the Planck time 10 to the power of negative 43 seconds, the earliest moment at which our physics can say anything meaningful about the universe. 1 part in 10 to the 62, 1 followed by 62 zeros. That is how closely omega had to match 1 at the beginning, not as an approximation. As a precision requirement imposed on us by the equations of general relativity applied to the expanding universe. Now, is there a physical reason for this? Is there some principle that would naturally set omega to exactly 1? In standard Big Bang cosmology, there is not. There is no symmetry, no conservation law, no known physical mechanism that drives omega toward 1. It is purely an initial condition. And asking why the initial conditions were so precisely tuned is, in standard cosmology, like asking why a bullet fired from an enormous distance hit an exact target the size of a proton. There is no mechanism. You have to assume it was aimed. The flatness problem connects directly to the horizon problem, and the two together make the case for inflation almost ironclad. The horizon problem is this: the CMB temperature is uniform across the entire sky to 1 part in 100,000. Everywhere you look in opposite directions across the sky, regions that in standard Big Bang cosmology were never in causal contact, separated by distances greater than light, could have crossed in the age of the universe at the time the CMB was emitted. The temperature is the same. How? Two regions that have never interacted cannot, in general, be expected to have the same temperature. If you put a hot cup of coffee and a cold glass of water on opposite ends of a very long table and they never come into contact, they will not equilibrate. They will stay at different temperatures. Yet the CMB is telling us that the universe achieved thermal equilibrium across distances larger than any signal could have crossed. In standard Big Bang cosmology, this is simply inexplicable. Inflation solves both problems with the same mechanism. Before inflation, the region that would eventually become our entire observable universe was small enough, much smaller than an atomic nucleus, that all of it was in causal contact. Thermal equilibrium could be achieved. Curvature could be smoothed. And then inflation stretched this tiny, smooth, flat, equilibrated patch into something vastly larger than our observable sphere. The CMB is uniform because the entire observable universe was, before inflation, a single, causally connected region, and the universe is flat because inflation drove out every trace of curvature from our observable patch and buried it so far beyond our horizon that it will never come back to haunt us. There is a third problem that inflation solves, sometimes called the monopole problem. In the extreme heat of the early universe, quantum field theory predicts that phase transitions should have occurred as the universe cooled, transitions similar to water freezing into ice, but occurring in the fundamental fields of physics rather than in molecules. These transitions should have produced exotic particles called magnetic monopoles, hypothetical particles with a single magnetic pole, north or south, but not both. Grand unified theories, which attempt to unify 3 of the 4 fundamental forces, predict that monopoles should have been produced in enormous numbers in the early universe. But we have never detected a single one. Either they do not exist, which would rule out a large class of unified theories, or something diluted them to undetectable concentrations. Inflation dilutes them perfectly. If monopoles formed before inflation, the subsequent exponential expansion would have spread them across such an enormous volume that the expected density within our observable universe today would be essentially 0, consistent with what we observe. 3 unsolved problems in classical Big Bang cosmology. One mechanism, inflation, that solves all 3 simultaneously. This is not the usual story in physics, where you get one solution to one problem. This is a single physical process that resolves 3 independent paradoxes with one stroke. That is powerful. That is the kind of convergence that makes physicists take a theory very seriously even before it has been directly confirmed. But as we keep returning to, every solution has a cost. Inflation solving the flatness problem means inflation stretched our observable patch out of a much larger region. Inflation solving the horizon problem means that the regions now beyond our horizon were, before inflation, part of the same small patch that equilibrated with ours, and inflation pushed them past the boundary. Everything that was originally in causal contact with us, that shared our early equilibrium, that experienced the same smooth initial conditions, most of that is now permanently beyond reach. We are living in a fragment of what was once a unified whole, and the fragmentation was permanent. Part 6. Inflation, the expansion that hid reality. The story of inflation begins with a problem that has nothing to do with flatness or horizons. It begins with Alan Guth, a young particle physicist who in the winter of 1979 and 1980 was working at Stanford, trying to figure out why we had never detected magnetic monopoles. He was not thinking about cosmology in the grand philosophical sense. He was thinking about a very specific prediction of a very specific class of particle physics theories, and he was troubled by the mismatch between what those theories predicted and what experimentalists had found in accelerators and detectors. The solution Guth arrived at what he called a spectacular realization, according to his research notes from that period, was that a brief period of exponential expansion in the early universe would not only dilute monopoles to undetectable concentrations, but would simultaneously solve the flatness problem and the horizon problem. He published in 1981, and the paper landed in the field of cosmology like a stone thrown into still water, sending ripples in every direction. The mechanism Guth originally proposed has been refined significantly since then, but the core idea remains. In the very early universe, the dominant energy was not matter or radiation, but the energy of a field specifically, what physicists call a scalar field, which Guth modeled as the energy associated with a phase transition in grand unified theories. This field was stuck in what physicists call a false vacuum, a state that is locally stable but not at the lowest possible energy. Think of a ball sitting in a shallow depression on a hillside. The ball is stable for the moment, but if it were to get over the rim of the depression, it would roll down to the valley below. The ball is in a false vacuum. The valley is the true vacuum, the lowest energy state. While the inflaton field, as it is now generically called, sat in this false vacuum state, it had a peculiar property. It acted like a cosmological constant, a form of energy that permeates space uniformly and does not dilute as space expands. This is the same kind of energy we associate today with dark energy, but at an energy scale roughly 120 orders of magnitude higher. An energy so extreme that it drove exponential expansion at a rate that makes the current cosmic expansion look essentially frozen by comparison. The expansion is genuinely exponential, not linear, not polynomial, but exponential, meaning space doubles in size in some fixed, very short time interval, then doubles again in the same interval, then doubles again. If the doubling time is, say, 10 to the power of negative 37 seconds, then in 10 to the power of negative 36 seconds, space has doubled, 10 times growing by a factor of roughly 1,000. In 10 to the power of negative 35 seconds, it has doubled 100 times, growing by a factor of 10 to the 30th. The number that emerges from the models for the total growth factor is at minimum around 10 to the 26th, and in many models considerably larger, depending on the details of how long inflation lasted. To understand what this means for the relationship between inflation and the observable universe, it helps to work backward. The observable universe today has a radius of 46.5 billion light-years. Before inflation, the region that would eventually expand into our observable universe was smaller than a proton, perhaps much smaller, depending on the specific model. After inflation expanded it by that minimum factor of 10 to the 26th, it became vastly larger than the observable universe. The portion of the inflated region that falls within our observable sphere, the portion we can see, is a tiny fraction of the total volume inflation created. Andrei Linde, a Russian-American physicist who became one of the central figures in developing inflationary cosmology, introduced what became known as chaotic inflation in the early 1980s. Linde showed that inflation did not require exotic grand unified theory phase transitions. It could arise much more generically, from a scalar field with a simple potential, an energy landscape where the field starts at a high value, rolls slowly downhill toward its minimum, and drives exponential expansion during the slow roll. Chaotic inflation is robust and flexible, and it connects naturally to ideas about what might have preceded or surrounded our inflationary event, as we will explore later. Inflation ends when the inflaton field reaches the bottom of its potential energy. Well, the true vacuum and its energy is deposited into the particles of the standard model. This process is called reheating, and it is the moment that marks the beginning of the hot Big Bang as most people picture it. The fireball of matter and radiation that then evolved into galaxies, stars, and planets was not the beginning. It was what came after inflation ended. The Big Bang, in this picture, is not the creation of the universe. It is the thermalization of inflation's energy into ordinary matter. The universe existed, in some sense, before the Big Bang during the inflationary epoch as a nearly featureless, rapidly expanding expanse of vacuum energy. Reheating has observable consequences. The energy of inflation did not flow uniformly into matter and radiation. Quantum mechanics, which operates everywhere and always, introduced tiny fluctuations into the inflaton field during its slow roll. These are not engineering imperfections. They are fundamental. The uncertainty principle guarantees that no quantum field can be perfectly uniform. The fluctuations in the inflaton field were, during inflation, stretched from subatomic scales to cosmic scales by the expansion. After reheating, they became fluctuations in the density of matter regions, slightly denser and slightly less dense than average, spread across the universe at scales set by the rate and duration of inflation. These density fluctuations are what eventually grew, under gravity, into the large-scale structure of the universe, the filaments, sheets, and clusters of galaxies we see today. And their statistical properties, specifically their amplitude and how that amplitude varies with scale, are directly measurable in the CMB. The Planck satellite measured what is called the primordial power spectrum, characterized by a spectral index designated n sub s. Inflation predicts a nearly scale-invariant spectrum, one where fluctuations have roughly the same amplitude at all scales, with a slight tilt toward less power at smaller scales. Planck measured the spectral index as 0.9649 plus or minus 0.0042. The prediction of simple inflationary models is a spectral index slightly less than 1. The measurement is 0.9649. The agreement is extraordinary. Inflation also predicts primordial gravitational waves, ripples in the fabric of space-time, generated by the same quantum process that produced density fluctuations, but manifesting as tensor perturbations rather than scalar ones. These gravitational waves would leave a specific imprint on the polarization pattern of the CMB, called B-mode polarization. This has not been definitively detected as of the date of this script, though the search is ongoing with instruments like BICEP and the Simons Observatory. Detecting it would measure the energy scale of inflation directly, a Nobel Prize-worthy result, and almost certainly within reach of the next generation of CMB experiments. But here is the line that ties all of this to our central story. Every fluctuation that inflation stretched to cosmic scales, every perturbation that became a galaxy or a cluster of galaxies or a cosmic void, each of these was once a quantum fluctuation smaller than an atom. Inflation is the mechanism by which the quantum becomes cosmic. And while it was doing that for the region that became our observable universe, it was doing the same thing for the vastly larger regions that inflation stretched beyond our horizon. Those regions contain their own quantum fluctuations, their own density perturbations, their own structures that formed from the same physics as ours, that evolved under the same laws, but that we will never see. Inflation created both the universe we can see and the boundary we cannot cross. Part 7. The minimum size of reality. In 2011, 3 cosmologists, Mihran Vardanyan, Roberto Trotta, and Joseph Silk published a paper that attempted to answer a deceptively simple question. Given everything we know, given the measurements from Planck and WMAP and the whole suite of cosmological observations, what is the minimum size the actual universe could be? They used a statistical framework called Bayesian model comparison, which is a rigorous way of asking which hypothesis is best supported by the data, while penalizing hypotheses that require many adjustable parameters. They considered a range of models for the global geometry and topology of the universe, and they asked what minimum size was required for each model to be consistent with the observational data, specifically with the constraint that the universe appears flat to within the measured precision. The number they arrived at is the one we introduced at the outset. The universe must have a radius at least 251 times the radius of the observable universe. 251 times 46.5 billion light-years. That gives a minimum radius of approximately 11.7 trillion light-years. And the volume scales as the cube of the radius. So the minimum volume is 251 cubed, roughly 15.8 million times the volume of our observable sphere. 15.8 million observable universes, minimum, packed into the actual universe. Let's think about that for a moment. 2 trillion galaxies in the observable universe, multiplied by 15.8 million. The minimum total number of galaxies in the actual universe under this conservative estimate is around 32 sextillion, that is 32 followed by 21 zeros. Every single one of them invisible to us, not because our telescopes are too small, but because inflation pushed them beyond the boundary of causal contact. And these are not exotic, unusual galaxies. They formed from the same physics, the same initial conditions, the same quantum fluctuations stretched to cosmic scales by the same inflationary epoch. They are, statistically speaking, much like the galaxies we do see, ordinary, invisible, forever inaccessible. And 251 times the observable radius is, to be clear, the lower bound, the number you get from the simplest inflationary models, assuming the curvature is at the edge of the observationally allowed range. Most inflationary models, especially those where inflation lasted longer or began from initial conditions further from flatness, predict vastly larger extensions. There is a class of predictions under infinite flat universe models where the actual universe is genuinely infinite. Not very large in the way we might informally use that word, but infinite in the strict mathematical sense, extending without limit in every direction, with no boundary, no edge, no furthest galaxy, an infinite